your target today. What do we want to get from today? What's the whole point? We're going to talk about air pressure systems and how can I predict weather based on these systems. So if I said, hey, it's a high pressure system, what kind of weather is that going to be? You should be like, oh, Mr. Clark, high pressure, happy weather. Sunny, clear, nice skies, awesome. Or I said, hey, what's a low pressure system? Well, Mr. Clark, low pressure is lousy weather, rain, clouds, nastiness. Okay, so you need to be able to understand that. And global wind patterns. Oh, look at this. Global winds worksheet. So, catch the connections, and we move on. So, we're going to start out the day by trying to understand some basic concepts. One, how do we read a thermometer? Unfortunately, your generation is addicted to cell phones, and iPads, and iPods, and computers, and electronic watches. And I have had so many students not even know how to read a clock.
Oh, fail.
So, I'm going to take it as not common knowledge as when I was a kid on how to read a thermometer. So here's how you read a thermometer.
You can read the lines.
You have a little reservoir of chemical. Usually it's alcohol. It used to be mercury, but mercury is a transdermal neurotoxin. Bad for you, absorbed through the skin. So usually use alcohol now. The hotter this gets, the more it expands, the more it goes up the tube, and then we can read that measurement on both sides, either in Fahrenheit or in Celsius. Okay? Scientifically, we like to use Celsius, right? Because it's really easy to measure, because 0 degrees Celsius is what? Temperature at which water freezes. 100 degrees Celsius is what?
Temperature at which water boils.
The temperature at which water boils. Thank you, Donnell. Very good.
212 degrees Fahrenheit.
Okay. Now, what is the temperature in Fahrenheit that water freezes?
32.
32. And then 212. Okay.
212.
Now, the reason we use Celsius is because it matches with Kelvin, and it's a much easier scientific scale to use. Why does the rest of America use Fahrenheit instead of Celsius?
Because we're different.
The answer is very simple. It's a more descriptive scale for temperature. If I said it's 70 degrees outside, you guys would know exactly what I meant, right? You would know about how warm that is, about how you would dress, about how it's going to look outside. It's very comfortable, familiar. If I said it's 20 degrees Celsius outside, what would that mean to you?
I feel like it's 60 degrees.
Yeah, it's about 70 degrees.
Yes.
Okay, well, if we go from 0 to 20, a 20-degree difference in Celsius and Fahrenheit is a different scale. So it's 32 to 70, that's 43-degree change, or 42-degree change, sorry, as opposed to just a 20-degree change. So you almost have double as many points. So if you want to get really specific with Celsius, you have to say, well, it's 20.5, which they do in Canada and the rest of Europe. Americans just never wanted to make the switch, so we didn't. So all of our weather maps are going to give you readings in Fahrenheit and not Celsius. So we might be doing some conversions here. But you have to be able to read one of these on the test. Okay? Something else that you need to know about is a barometer. This makes sense. We want to measure air pressure. A barometer is a measurement of bar. B-A-R represents pressure. So this is a pressure meter. There are a couple different types of pressure meters out there. Barometer. Always good to use the term that you want to learn. You say it out loud to yourself a few times, it'll help you remember it.
Barometer. Barometer.
Barometer.
Pressure meter. Barometer.
Okay, the first barometers were what we call mercury barometers. And these things are really cool. They use a chemical called mercury. Actually, it's an element, mercury. And mercury is one of those neat elements that adds the pressure and temperature of the Earth, just nice normal air that we're used to on Earth. It stays liquid. I believe it's the only one that does. That's kind of cool. So it's a lot of fun to play with. And it acts like little bubbles of silver. It's often called quicksilver, but I called it a transdermal neurotoxin. The problem is that mercury will absorb into your skin. That's transdermal. And neurotoxin, or is your neurosynapses up here, it's a toxin. It will actually damage your brain, and you can go crazy, literally crazy, chemically, from the mercury. So thus, you're not allowed to see mercury in any high school ever, anywhere. They check our thermometers all the time to make sure we don't have mercury thermometers, because that's a bad thing. But in itself, mercury does some cool stuff. So here we have mercury in a tube. If you take the tube and invert it, and then stick it in here, it leaves a little gap at the top. Put your hand down. Okay? It leaves a little gap at the top, and that's actually a vacuum. Vacuum being there's nothing there. It's like space. There's nothing there. And well, that holds the mercury in the tube. So what happens is, on a high pressure day, there's more air pushing down, and that pushes on the mercury here, which pushes this higher in the vial. And as the air kind of backs off again a little bit, you get lower pressure, the air is rising, this is allowed to expand a little bit, and then this falls in the vial.
What? I'm lost.
Yeah.
Okay, this goes up and down based on pressure.
Gotcha.
Okay, we called that inches of mercury, and sometimes you still see inches of mercury. Now this is what, we don't use these anymore as far as what we're going to be using, and even in the climate world and the weather world, they don't use inches of mercury really anymore. We use a system called millibars. That's the metric system for pressure. Okay, so, but I want to show it to you because it's kind of cool. Now, over here is what we're going to be using and understanding. Sammy, stay awake. Okay, if you have to, you're going to stand in the back. This is an aneroid barometer. Aneroid barometer. I have no idea where it comes from, but it's an aneroid barometer. What you need to know is it's a small watch type thing, or if you could take your speedometer out of your car and just thunk on the countertop, that's kind of what this would look like. It's got a dial starting here, working its way over here. Usually it has writing on it like clear, happy, rainy, cloudy, something along those lines, because you can predict weather based on air pressure. So, the higher you get in the numbers, the higher the air pressure, blah, blah, blah. Now, Amber, which one of these do I use to measure pressure?
A barometer.
Well, yes, the barometer, but which of these lines is that one that's actually pointing to the pressure?
Today?
Okay, so here is the gold one, so I got some votes for gold. What do you think, Amber?
What was the question? Yeah, I've been thinking.
Okay.
Is that like what it feels like versus what it is?
I think it's the
Okay.
long black
The
one.
right answer is the black one.
Hey! I knew it!
Okay, now this really confused my students last year, so I'm really trying to make sure you understand this. Let's look at our clock up on the wall. If we look at our clock, we have the long hand and the short hand, right? You see how it's got a little bit of a tail end on the back of the hand?
Yeah.
Okay, that's common with a lot of devices, either to give a counterbalance to the hand itself. For whatever reason, they often have little tails. So this black is just a tail for this wand, and this is actually the dial. So this going back and forth will tell you what the pressure is. So what the heck is this gold thing?
Seconds.
Alright, I'll give you a hint. You can actually adjust the gold thing yourself.
Oh, this is what it was yesterday.
Yeah, you can actually set this to whatever you want. So if the pressure's right here today, I could turn this dial and it would move the bar over here. And then in a day or two I can see, oh, how is the pressure changed? And that's all that is. So when you go to read the pressure, please look at the one that looks like a wand, like a Harry Potter wand, okay, and where it's pointing. So here's 1020, 1025, 1030. Can you guys read what this pressure is?
10:26.
Well, 1031 would be over here.
10:26.
1026. Okay, so that's how you read an aneroid barometer. Very good. Moving on. Okay, now to understand air pressure, you have to understand wind. And wind and air pressure kind of go, you know, they're hand in hand, they're tight. Why? Because as air goes from high pressure to low pressure, the air actually has to move sideways. And as it moves sideways, we call it wind. So the movement of air from one spot to another to balance out a pressure difference that's caused by the Earth being heated unequally is wind. Now take your brains back with me to the soil and water lab. Okay? We had the dirt, we had the water, we had the lamps, and we learned, hopefully, that the water heats up slower than the dirt does. Dirt heats up really, really fast, and guess what? It also cools off really, really fast. Water just kind of takes its time heating up and takes its time cooling off. Water has high specific heat. It takes more energy to heat it up. It takes more energy to cool it off. So it acts like almost like an insulator. It holds on to its heat very well. Now this is really good if you live by the beach. You won't get these extreme temperatures. Okay. Deserts. Have you ever heard that in a desert at night, what does the temperature do?
Cold.
It gets seriously cold at night in a desert because there's no water to help temper the temperature. It gets really cold. In the daytime, it's seriously hot. Why? Because dirt heats up really fast and then cools off just as fast as it heats up. But if you live in a beach town, that's not the case. It will only get so hot because the water helps keep the temperature kind of even keel. And at night, the water adds a lot of heat to the air that would normally be lost as it cools off. Good thing about water. So that's what we learned there. So there's some things that affect the wind. The pressure differences. The bigger the pressure difference, the greater the wind. If you have really high pressure and really low pressure, the air is going to be moving quickly to equalize itself. For example, you blow up a balloon, you can get this big balloon, and you let it go. Well, that's really high pressure in a balloon. You let it go, what does the balloon do? It's flying all over the room as it's trying to equalize the pressure with the outside of the balloon. That's creating a little wind out of the balloon. That's wind. So that's pressure differences. And then you have this goofy thing called the Coriolis Effect. The Coriolis Effect. And we have friction. The Coriolis Effect, we're going to talk about that in a slide. Friction is simply as the wind moves across the ground, the ground that it's moving against is pushing against it and pulling it back. So it doesn't go as fast as it could go because there's friction. That's not as big of a deal, but the Coriolis Effect and the pressure differences are huge. Okay? Ready for me to move on? You got anything? Okay. So before we talk about the Coriolis Effect, I want to talk about the pressure differences. So, here I have a low pressure system and a high pressure system. You know, this looks like maps we've done before. Where have we seen these maps before?
Topography.
Topography. Topography. Okay. So here we have 1004, 1000, 996. Wait a second. What is the contour interval on this map? 4 millibars, because that's the unit that we're using here. Remember how I said we use millibars with pressure? 4 millibars. Well, 996 is actually really low pressure. You can have low pressure systems that never get below 1000. So 996, pretty low. And then over here we have 1028. That's pretty high. So what you should be looking at here is a map just like a topographic map. Here you actually have a valley of air. And here you have a hill of air. It's really heavy pressure here, higher pressure here, and lower pressure here, and they're trying to equalize. And as they do that, they're getting pushed by wind, and they move across the globe. High pressure, low pressure. Well, one of the things we learned in mapping was that the closer the contour lines are together, the steeper the hill, right? Do you remember that? And over here, these are all really spaced out, so this isn't very steep at all, is it? Well, if Fatima started rolling down a hill, if it's a really steep hill, as she's yelling, "As you wish," going down the hill, okay, if it's a steep hill, she's rolling really fast. Well, if it's just like a nice gentle bunny slope, like a ski slope, where you have to push to go, you're going to fall down and then get right back up because it's not steep, right? Well, the wind does the same thing. Here, where the pressure is just kind of like, there's not much of a pressure difference. Look at this, there's no wind. You see the tail feathers here? There's none, there's no wind. But where is it really close together? Oh, these are closer together. Look at these tails. I have a triangle and a small flag, or a small feather. Do you remember that the triangles equal upwards of 50 knot winds, and the small flags are about 5 knot winds? So here I have 55 to 60 knots. The wind is booking. It's going fast. Right? So here's a steep pressure, wind moves faster, than here where it's just kind of chill. Because the bigger the pressure difference, the faster the wind moves. Okay, that's the first thing I want you to see here. Remember back to the quiz, cyclones, or low pressure systems, move counterclockwise in and up. How do I know that from this map? Well, look at the direction the wind is going. The wind is going in this direction. What direction is this? As we go around and around like this.
Northwest.
This is counterclockwise, right? Because a clock, if you look at our clock, goes around like this, right? Counterclockwise is just the other direction, going the other way. We look here, and you see how the wind is moving kind of in toward the low pressure? It's going in toward the low pressure as it's going clockwise. And here the high pressure system, the wind is actually moving away from the high pressure system, and it's going clockwise. This is going counterclockwise. That's what I want you to see there. So first thing first that affects the wind, pressure differences. Are we good with pressure differences?
Yes.
You guys are awesome. Okay, Coriolis Effect. You guys don't look nearly as excited about this as I am. Okay, that's fine. Coriolis Effect. I want to get in a plane on the North Pole. If you could do this. I'm going to get in a plane on the North Pole, the very top of the Earth, and I'm going to start a 12-hour flight or so, or longer, and I want to fly down here toward what looks like the Galapagos Islands, off of the coast of South America. And I'm flying straight for the Galapagos Islands, and I figure out where it is before I leave, and I just start flying straight as an arrow. 12 hours later, what has the Earth done?
It's moved.
The Earth moved. I'm still going toward those Galapagos Islands, but the Earth has actually rotated under me, so by the time I get to land, I'm like, oh, crap. There's no islands here. The islands are over there. I missed them, because I tried to go straight, and the Earth moved under me. Now I'm in the middle of the Pacific Ocean somewhere. As I did this, there's a force that we call the Coriolis Effect, or the Coriolis Force. Now there's a lot of other things that go into this, like friction and wind and all, but just the very basics. If I try to go in a straight line and there's something under me that's moving, I'm not actually going in a straight line. I get curved or I get bent. So, I have a video that I want to show that I think helps. Okay? Nice little quick, like, minute video. Here we go. I'll probably show it 3 times.
Yay.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
See, that's why we're going to watch it again, because I want you to kind of think about that and absorb it. So try again.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis Force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
Is that starting to make a little bit of sense? So the Coriolis effect is simply that you're trying to go straight, but the Earth moved under you. Well, this has a very specific impact on wind. On wind and really a lot of things, but we're going to talk about just wind today. Okay, so let's go back. Let me pull this off the screen, and we'll go back to here. So the Coriolis effect. Now specifically, how does this specifically work? Well, if you have wind trying to go from a high pressure to a low pressure system on the globe, it's trying really hard to get there. But it doesn't ever get from the high to the low in the way it would like to go. Straight. It gets bent because the Earth is rotating under it. And in the northern hemisphere, it gets bent to the right. In the southern hemisphere, it gets bent to the left. Now, do you guys know what direction a cyclone rotates? Remember the quiz? Cyclone. Counterclockwise. And you might occasionally hear me say counterclockwise in the northern hemisphere. In the southern hemisphere, it gets bent to the other direction. So a cyclone or a hurricane in the southern hemisphere rotates clockwise. It's completely backwards. Okay, I'm going to skip the friction part. So let's talk about this really quick. Anyway, high pressure system versus low pressure system. This is very important that you get this. Very important that you get this. In a high pressure system, the air is moving down. Do you guys remember how we drew convection and we drew all those convection cells? Any place where the air is coming down, when we're talking about wind, it's high pressure. Any place where the air is rising because you've added heat to it, it's low pressure. High pressure, down. Low pressure, up. Now, high pressure, I'm actually going to talk about the low pressure first, then we'll go back to the high pressure. So low pressure systems, we call these cyclones. Cyclones. Well, Akuba, if I said to you, there's a cyclone coming, does that invoke in your brain images of nice weather or bad weather? Bad weather. Cyclone, bad weather. Now, whether this is a full-out like tropical cyclone or a tropical typhoon or a hurricane, or it's just kind of a low-pressure system moving its way across, cyclone invokes images of bad weather. Well, in a cyclone, the air is going what direction? Up. Rising air, cyclone. Counterclockwise fashion in the northern hemisphere. Okay, here's the bread and butter of our first learning target. Well, I want to be able to predict the weather based off pressure systems. Well, low pressure, cyclone. The air is going up. Now, based on what we learned last class, that air rising gets colder, right? The higher it goes, the colder it gets. Do you remember that?
Yeah.
Somebody remembers. The higher the air goes, the colder it gets. The colder the air becomes, the less what it can hold. Water. Good job, Ingrid. The colder air gets, the less water it can hold. Eventually, it will get saturated and form a cloud. Clouds give us rainy weather. Well, look at this. Low pressure. The air is going up, so the air is rising. And the more the air rises, the more blank you get. What do you get when air rises? You get clouds. So should it make sense that as low pressure systems developed, they form kind of wet, rainy weather. Do you see that? If air is rising, it's making clouds. The more air that rises, the more clouds you get, the more rainy, wet weather you get. So if you think back a couple weeks ago when it was just kind of rained all week and the ground was just soggy and cold and wet and rainy and completely overcast,
What's gonna happen this week?
low pressure system. Okay? Yeah, it's not my favorite either. High pressure system is the exact opposite. High pressure system is the anti-cyclone. Francisco, what does it mean if I put the prefix anti in front of a word?
Bad.
Francisco.
Oh.
What? Before, it's not before, it means like the anti is the opposite of something. So it's not a cyclone, it's the anti-cyclone. It's the reverse cyclone, or the not cyclone.
The bad.
Okay, Maria, you get that? Okay, so the anti-cyclone is the exact opposite of this lousy weather. So, low pressure, lousy weather. High pressure, happy weather, right? It's H for happy, L for lousy. High pressure, happy weather. Why? Because the air is not going up, the air is coming down. And as the air comes down, it is getting warmer because it's getting compressed. It's getting warmer, there's more room for water vapor. It's getting warmer, there's not typically any, starts with the C, clouds. If there's not a lot of clouds because the air is coming down, you tend to get nice weather. Now it can be really windy, like this weekend was pretty windy, but it was really nice weather. It was clear, it was sunny, it was just generally a really nice weekend, to the point that your teacher even got a little sunburn on his hands. So, nice weather, because that was, what? Saturday. Saturday I was horseback riding, and I wore a shirt up to my hands, and this part of my hand got a little bit of sunburn. So, pressure centers. Okay? Does this make sense? Does this make sense? Okay. I hope so. I really want this to make sense. If it doesn't, let me know. I say hint, hint, cough, cough. I wonder why I would say that.
It's on its head.
Moving on. Okay, I just want to kind of demonstrate this again. Low pressure, lousy weather. High pressure, happy weather. Okay, do you see how the air is coming in and up in a counterclockwise fashion? And here it's going down and out in a clockwise fashion. Very important you can see that.
Is that a mountain?
Is what?
Is that a mountain or like
Yeah, these are the
rocket?
well, these are the Rockies, these are the Cascades, the Sierra Nevadas. This is a mountain belt, yes, lots of mountains. Okay, I'm gonna skip that. The big thing about this one is, as air is moving down here, air is also moving up here. And this is where we get our jet streams, where the air is moving from high pressure to low pressure in the clouds. You get rivers of air up here, and that's where you get the jet stream, or quite literally, a kid could put a balloon filled with helium, and it goes up in the sky, and he puts a little message in it. This actually happened. And the balloon got into the jet stream pulled it across the country, and it eventually popped, and the balloon comes down, and some other kid found the message, and like they set up a little pen pal relationship type of a thing. Jan, what's up?
Do you know that?
What?
Do we need?
Guys, I asked Jay a question.
Do we need to know that?
I'm not going to really focus too much on this. I just want you to get that the jet stream is part of this whole process. Okay? But this you have to know. Okay, let's take the Earth and put on the brakes. Okay, Earth is stopped. We've stopped all rotation. We're no longer having days and nights. The Earth is no longer moving. If we could do this, we can't, thank goodness, because it would kill everybody. But if we could do this, what would the weather look like? What would the wind be doing? Well, the equator gets a whole lot of energy from the sun while the poles do not. Because the sunlight coming to the equator hits at a 90-degree angle. It's just directly sunlight straight overhead. It's very direct. You get a lot of energy from the sun all year round. The sunlight coming to the poles, the angle is much, much wider. It's indirect. So that same amount of energy is spread out, and you don't get as much energy. So direct and hot, indirect and cold would be a good way to think about that. So if the equator is receiving the most energy and the poles are receiving the least energy, what area is heating up faster? The equator. If the equator is hot, what happens to air when you heat it?
It gets hot.
It gets hot, and then it
Moves.
Evaporate.
where'd you see?
Oh, air, never mind.
Where'd I put happy?
Next to D-Lo, speed division.
Right here.
Oh no, yeah, here.
What?
Okay, seriously. We can talk. Okay, so here we have really, really warm equator air. This warm equator air is heated. You heated it. What happens to air when you heat it? It
Rises.
rises. So Donnell,
Yes, sir.
genius of the day,
Yes, sir.
Are you doing squares?
low pressure or high pressure? Which one has rising air?
Low.
Low pressure has rising air. So here we have, I'm going to come, weather maps use colors. I'm going to try to use these colors as well. Low pressures are always red. Low pressure system. So the air is rising, it goes toward the poles, it starts to sink. You get sinking air. So, Tatiana, air that is sinking and coming down, is it high pressure or low pressure? It's what? High pressure. Air always goes from high to low. Right? Remember the balloon. If you blow a balloon up, it's pressurized. It's high pressure, and then you let the balloon go. Does it start getting bigger and more pressurized? No, it tries to equalize itself. So it always goes from high to low. So the air wants to go from high to low. Do you see how the arrows show that? The air wants to go straight down. Problem. Remember how I said, oh look, I'm at the North Pole and I want to fly to Ecuador or to the Galapagos Islands. What's going to happen when I get here? The Earth has turned, and because the Earth has friction, it's pulling the winds with it as it turns. And as the Earth pulls the wind with it and it turns, it gets deflected, and the wind moves to, in the northern hemisphere, the wind moves to the
South, west,
right,
north.
left, right? It moves to the right. So the wind will end up moving to the right. Okay? Let's talk about that in a little bit more detail where you can see it a little bit better. By the way, this whole idea of direct versus indirect, equator versus poles, test question, you have to understand why the equator has more energy than the poles do. You got your notes, Happy? Okay, just because you come late doesn't mean you get to slack off. Yeah. Okay. Now here is a little bit more complicated picture. Okay, I said I wanted to cover this in more detail. This is it. Okay. But this don't freak out. Don't freak out. The equator has low pressure systems, right? Why is the equator low pressure? Because it's hot. And what happens when you heat things?
Pressure goes up.
Pressure goes
Pressure goes down,
Yeah.
low.
and they actually the density goes down, and when the density goes down, there's less pressure they rise. I'm sorry, I'm trying to get everyone here. So these are low pressure systems. I can't see that at all. I'm gonna go back to black. Low pressure system. All right, Steven. I apologize for missing your hand.
No.
Is that a question?
No, it
Okay.
was more of a statement.
Where is the high pressure system, Steven?
It is
If this is low, where's the next high?
at the,
Here?
yes.
Okay. You're right. If the air is rising here, it's sinking here. The air is rising here, it's sinking here. Right? Because air that goes down is high pressure, air that goes up is low pressure. So I could just do, it just alternates. And I can't see the bottom of the globe, so I'm going to stop that. Do you guys get that it alternates?
Yes.
Thank you. Wait a second, I said that wind goes from areas of high pressure to low pressure. Here's how you figure this out, because you're going to have to figure it out for the test. Okay, if the air is trying to go this direction, because it always goes from high pressure to low pressure, it wants to go straight. Can it go straight?
No.
No, so I'm going to turn this into a dashed line to show where it wants to go. But it doesn't actually go there. In the northern hemisphere, it's deflected to the right. So, okay, so this is the left of the line, this is the right of the line, it's deflected to the right. Oh wait, do you see how the wind here is going to the right?
Yeah.
Aha!
That's the left.
Up here, it's deflected also to the right. Right, because the wind wants to go straight from like Florida up here toward Canada, but it can't go straight because the Earth is rotating. And that drags the wind to the right in the northern hemisphere, Coriolis Effect, and we get the prevailing westerlies and the northeast trade winds. And up here, the wind wants to go straight here, but we know it can't go straight, so it gets diverted, once again, just right down here, to the right, and then we have the polar easterlies. So why is the wind in certain belts of the globe going not straight up and down like we'd expect it to, but to the side? Coriolis Effect. Okay. This is, Coriolis Effect's a hard thing to understand, but is this starting to make some sense?
Yeah.
A little bit? Kyle? Montoya? Yes,
When
Ingrid.
we read left to right, you want us to read like front words because you're saying it's like that way.
Left, if like where the arrow is pointed, if the arrow is pointed this way, it goes to the right of the arrow.
That's my left.
Okay, so but I'm pointing at you, so it's my right. If you're facing this way, the arrow is going that way, so it's to the right of the arrow.
Okay.
Right. So if you were, this is like where you're sitting, this is where I'm standing. So this is your arrow. So that would be to the right. But this is where I'm standing, look at you. So my arrow is pointing at you, so that goes to the right this way. Does that make sense?
Yeah.
Okay. I want to practice this again, so I put in a slide. I cheated. I took the image off the test and put it in the slideshow.
That's not cheating.
Yeah,
Okay. This is what I'm expecting of you. I want you to be able to take this picture and turn it into this picture. Oh, no. Kind of crazy. Okay. How do you do this? This is how you do this. Once again, I'm going to try to do the color coding to make it a little bit easier. Dominique, stay away. Okay. Where do we get the most energy to the Earth?
From the
What line of the Earth? The equator. If the equator is getting the most energy, it's getting the most heat, right?
Yeah.
What happens, Syed, when you heat stuff? gets really hot, and what does hot stuff do? It rises. Wait a second. What pressure systems have air that rises? Low or high? Low, the air goes up. High, the air goes down. So I can automatically say that this is probably a low pressure area. So once I know the lows, all I have to do is alternate to get the other ones, right?
That means that's H.
Okay, so if this is low, this is high. This is low. This is high. This is high. This is low. That's high. Does that make sense, Maria? Okay. Now, all you have to do is say, hey, wait a second. I know that air always flows from areas of high pressure to low pressure. Okay? Air wants to go straight. Can it go straight?
No.
No. So here we are in the southern hemisphere. Air wants to go straight. It wants to go just like this. But it can't. It just can't because the Earth is rotating. And that pulls the wind. So it's deflected in the southern hemisphere. What direction?
Right.
Southern hemisphere
Left.
goes to the left. Okay, Ingrid. Okay, where you're standing, facing the board, what direction is it going to go? This way or this way? If it's being deflected to the left, is it the wind going to go this way or this way?
The wind's gonna go that way.
That's right. That's right. The wind goes this way. That's deflected to the left of this line. Okay? So you can even draw these in. So here's the first thing I'm going to ask you to do on the test. Draw with arrows the wind belts. Okay? Well, high pressure to low pressure. Okay? Now what direction is the wind going to be deflected? In the northern hemisphere. To the right. So if I'm facing you, the wind goes to the right. Right?
Oh, right.
So, yeah, go right. Yeah, there we go. So it goes to the right. And if you want to double check yourself, these arrows always point at each other.
Okay.
Okay, so we can just draw a couple of those arrows in. Hey, there's the trade winds right there. Woohoo! We call these the northeast trade winds. What do you think these are? What kind of trade winds?
The south.
South
Okay.
east. Very good. Yes, you may. You're welcome to. Okay. So this is one part of the picture. Let's see if we can fill the rest of it in. Fill the rest of it in. Okay. The air wants to go from high to low. So what direction is it deflected in the northern? Yeah, that's right. So it goes that way. Right, because you're facing me, northern hemisphere goes to the right. So then we draw some arrows like this. Same thing down here. Draw your arrow. It's deflected. Oh wait, it's deflected to the left in the southern hemisphere. So if I'm facing you, what's my left? This side, right? So it's going to go to the left. If you want to check yourself, your arrows should always kind of go at a diagonal to each other. Yeah. We call these the winds that come primarily from the west. We call these the...
Why is it the west?
Why is it the west? Because they come from the west. The westerlies. And we have two more that we have to fill in now. So we have to go from another area of high pressure to low pressure. And now it's just becoming kind of habit because we know the lines, it should look like this. So you have lines that come like this. To the left. Yep. These are coming mostly from the east. We call these the,
Eastern.
yeah, that's right, the polar easterlies. Okay, that's 2 parts of a test question on the test. In fact, I'm going to devote an entire page to this concept.
How many points is that?
I don't remember, but it's a good chunk of the test. Okay, there's another question right after this that says, wait a second, you know the names of the wind belts, you know the direction the wind belts go, but do you know the climate zones that the wind belts are associated with? And that's actually going to be really easy for you guys. Why? Because you're geniuses to start with. I'm going to use a blue line here. The area between the Tropic of Cancer, the Tropic of Capricorn, and the Tropic... I always get them back mixed up. So well, I'm not even going to bother looking for it. Okay, between the Tropics of Cancer and Capricorn, you have the equator. And this part of the Earth gets a whole lot of solar energy. Summer, winter, winter, summer. It's always kind of summer. Which is why if you go down to Costa Rica, Honduras, and all these Central American countries, it's always really warm and they grow lots of bananas and pineapples and papayas and mangoes, right? Because these are things that need heat and moisture. Okay? We call these the, starts with the T,
Tropical?
tropical. These are the tropical. Tropical, the tropics, the Caribbean, the tropics. Okay? If we go up here, there's another zone right here that's on the between the tropics and the last one. Okay, so we got the tropics. Whew, that was hard. We got the tropics. Now, what's at the very top? What is the air like at the North Pole? It's cold. Yeah, it's we call it. Starts with a P. Polar. Once again, very different.
That's all?
Okay, there's one more in the middle. If you have somebody who's really kind of blows up and is angry all the time, can't hold in their emotions, and every time you look at them they're screaming mad or really happy, they're, well, bipolar. We call them hot-headed. Someone's hot-headed, as opposed to someone who's just kind of like overly chill, and they don't know any other word in their vocabulary other than chillax. They're just way too laid back. If you want to know somebody who's just kind of in the middle, that person is temperate. They have just kind of a temperate personality. They know how to get going and hot, but they can control it. And they know how to be chilled, but they're still getting stuff done. That's a temperate person. If you want to temper your eggs, you are slowly heating up your eggs instead of getting really hot eggs really fast. So, I'm trying to define a word for you here called temperate. So I'm going to write that here. Temperate. The temperate zones describe an area that gets hot in the summer and cold in the winter. This is typical 4 seasons. You have a nice, pretty 4 seasons. Here in Virginia, we are like right smack dab in the middle of the temperate zone. Well, not smack dab in the middle, but it's close to it. Temperate zone. We have a distinct summer. We have a distinct winter. And we have a very clear spring and fall. We are in the temperate zones. We get really cold, we get really hot. The polar zones, they just stay pretty cold most of the time. They start to warm up a little bit in the winter, but if you go to like Alaska, like up into Nome, Alaska, really, really far into the poles, they're like, yay, it's summertime, it's 45 degrees, woohoo, heat wave, right? That's what it's like up there. Okay, even summer doesn't get that hot. And in the winter up in the poles, it's like -20. Just a little bit of a breeze. It's a little cold. Okay, because that's what it's like up there. Well, down here, like in the Bahamas or in Central America, Panama, it's like, woo! Oh, it's hot day outside. What is it? 120. Okay. Oh man, it's cold today. What is it? 110. Okay, it's regulates very, very hot all the time. As far as the temperate zones, what's a hot summer for us? Getting close to 100, and a cold winter, it's freezing outside, snowing. So that'd be temperate. Okay? I want you guys to know that these are 3 test questions for you. Boom, boom, boom. Draw the arrows, label the wind belts, and tell me what the climate zones are. And that's a big part of understanding weather, where weather is. Okay, and that's going to come into play when we talk next class about air masses and where the air mass comes from. If you can understand this, you'll be in great shape. Okay, so we're building our knowledge here. Building our knowledge. Okay, we are making great progress. I'm sorry this is taking so long, but you're doing really good.
Are we almost done?
We are getting there.
What time does class now?
We are almost done. In fact, we're so almost done that I have 2 more things to explain and I'll be done. Okay. Normal time. Okay. We're going to take our knowledge from the Soil and Water Lab. Okay, let me see if I can draw this quickly. Okay, so here's your umbrella. You're at the beach. Now, Syed decided to go to the beach. Because, great thing to do. Now, Syed, he gets really bad sunburns, so you guys know. So he takes, that white zinc oxide, puts it on his nose, and they get these really big brim hats, and he's got these white polka dot and pink shorts, and water wings, because he's got to have the inflatable water wings, and then the inflatable tube around his waist. So he steps out out of the car, parks the car, and steps into the sand on a really hot summer day. Ooh, let me get my son. It's a really hot summer day. Okay. He steps barefoot into the sand. What does that feel like?
Burning.
Ow! Why? It's hot. The sand is hot. So he duck foots it across the sand because he's wearing all this gear. Gets down toward the water. The sand is getting wet and feels good on your feet. And then he gets into the water, and the water is nice and warm, but it's not nearly as hot as the sand is, right? The beach. You guys have all experienced this?
Yeah.
Okay. So here's Syed's little kind of station here. And he's got his Mountain Dews and his iced teas and whatever beverage he's drinking. The sand is hot, right? Sand is so hot it burns your feet hot. And you go down to the water's like, cool water. Or maybe even it's early in the season and it's cold water. Okay, or way colder than the sand is hot. Remember what I said about the deserts?
Yeah.
Okay? During the day, the sand is really, really hot. So, where is the air rising? Where's the air going up? Over the ocean or over the hot sand? Hot sand, because hot stuff heats the air, which causes it to rise. So this air is rising. Okay? Any place we have rising air, what's the pressure?
Low.
Low pressure. Okay. This air starts to move this way, starts to get colder. It gets colder, comes down. Now we have cold air, and now we have a high pressure system because it's air coming down. And then that air has to replace that air that's leaving. And we get a breeze. We get a little bit of a wind. So if you stand on the beach, one of the nicest things about the beach is it's always breezy. Like, oh, there's a very nice, cool breeze hitting my face. Wait a second, that should make sense. Here's cold water. So the cold water is cooling off the air, so by the time it hits you on the really hot beach, it's cooled off. Like, so nice. Well, what do we call a breeze that comes from the ocean? Ocean breeze. So you can either call it an ocean breeze or a sea breeze. I've even heard it called a water breeze. Okay? Does this make sense based on everything that we've talked about? Does that make sense? Okay? Do you see how to put the high and low pressure in? You see why it's high and low pressure?
Yes, high pressure goes down, low pressure goes up.
That's because you are ingenious.
I
Okay?
should dream about that.
I'm dreaming about that. Okay. Alright, let's say, so here's Syed, he's gotten out of his duck-footed garb, and he decided, you know what, I'm gonna go walk the beach at night and just enjoy a moonlit stroll. So he goes out at night by himself, because it's always best to go by yourself to the beach at night. Always best to go by yourself to the beach at night, be good. Okay? He's going on a nice stroll at night, and now the sand is not so hot. It's like the desert. The sand has really cooled off because it's lost all of its heat. And he said, you know what, this sand is kind of cold on my feet. I'm going to go walk in the surf, or in the where the waves are crashing. And now the sand is kind of warm because the water at night doesn't lose its temperature. Every night the water doesn't change temperature, it just kind of stays even keel. So now the ocean is warm, and the sand is
But like if you go to the ocean,
cold.
it's hotter.
I'm talking about just kind of general summer day. Okay, so the ocean's going to be warmer, the land or the sand is going to be colder. Now, Montoya, since you seem to get this, where is the air rising?
Is it night?
It's at night. Yep.
Okay, then I guess it's right. It's going. No, it's going up.
Yes, it is going up, but where is it going up? Over the land or over the ocean?
The ocean.
Ocean. Did I hear you say that? I heard you say that. Okay, it's rising over the ocean, right? Because this is where it's warm. So this is where the air is rising. So the air starts to come like this. All right, we're just going to draw our convection cell.
And then it goes down to the land, so it can be even with the temperature.
Yeah. So now the last thing we have to draw in here to make this complete is where is our high and low pressure? Actually, two more things to draw in.
That's low.
This one's low.
One's low.
Why is this one low, Ingrid?
It's going up.
Because it's going up. Exactly. Oh, this class keeps going until normal times. We will be done before the end, I promise. Okay, I know these notes are long, and I really am sorry about that. I don't like making this long, but we really are out of time. So keep your speed pencils on. Okay, what do we call this? If the breeze is coming from the land, it's a land breeze. Land breeze, okay? Do you guys ever notice, like, if you, like, I noticed this at Ocean City, because Ocean City has, like, swamps behind the beach, on the inland. I loved it, I had a blast. So I went to Ocean City, and when, at night, the land breeze, there were a whole bunch of bugs on the beach, because they were being blown in at night. It's kind of cool. I would heartily disagree with you, but that comes from somebody who used to live a quarter mile from the beach in California.
I have not lived that close, but I'm still California beaches.
Okay. Okay, so you guys think that, I'm not going to make you do it now, but do you think you could fill this out on your own now?
Yeah.
Okay. Okay. I'm skipping this because this is very simple. Guess what? The United States lives in a temperate zone where the air always comes from the west. The wind always comes from the west. So our weather comes from west to east. Woo! Alright, moving on. I have two more slides to show you and then we're done with the slides. And these are really, really, really easy to understand. Okay. The trade winds blow really hard, really strong. And that pushes the water to Australia, Papua New Guinea, Singapore, the Philippines, Indonesia, blah, 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 blah. Okay? Hot, warm water. Because the sun hits here. It gets hot, it gets hot, it gets hot. Like here's Hawaii right here. And all of this water piles up and piles up and piles up here. This is why this is known for being a jungle. This is jungle conditions. Okay, over here, cold water, desert condition, like the Atacama Desert and all that stuff down here.
Does this know the low?
What about the, where's New
I don't know. Where's New Zealand? Here. Okay,
Is it cold or?
New Zealand is beautiful. But New Zealand's like going to England. It's like England's up here, New Zealand's down here. Now, this is La Nina, or the girl, right? Okay,
That was the kid.
La Nina, it's the girl. And this is normal conditions. Sometimes this normal conditions gets even stronger, and that's really what they're talking about with La Nina. Well, remember how I said that the air that's moving high in the sky is what we call the jet streams? And that's a river of air in the sky? Well, that controls how our weather moves across America, from west to east. But every now and again, I think it's every few years, maybe every 5 to 7 years, it's not exact, the trade winds kind of break down and they don't blow as strong. You know, when the trade winds don't blow as strong, the ocean's not being pushed over here, and all this warm water makes its way back to Peru. And when that happens, the cold water coming from Antarctica kind of shuts down a little bit, and it gets really warm over here. And that changes the way that the warmth gets up into Canada. And Canada gets really warm winters, alright? Right? I can't even do that well. So Canada gets a really warm winter, but that brings the jet stream and it dips down. Hey, guess what happened this winter? Okay? I'm not sure if it's El Nino or not, but this is actually what was happening. The jet stream dipped down, picked up this wet water, and socked it into us all winter long. And we had a really wet, really cold winter. Okay? So this is El Nino, or the boy. Okay? I don't know. I didn't name it. I didn't make the decision. Okay? That's all I have for you today.